Hello, welcome back. In this lecture, I would like to describe an important quantum circuit that is called a swap test. A swap test circuit solves the following problem. If we are given a 2-qubit register, so we have register 1 and register 2, how we tell that the two registers are in the same state? We don't want to, and we can use the destructive read that destroys the superposition. And also, we're not really interested in the specific knowledge of the state of the quantum system. We simply want to know if they are different or how much different. So the problem that the swap test circuit solves is, without telling us what the quantum states are, just let us know whether the two values in the quantum register are equal or not. The swap test circuit is actually the following. We have 3 quantum register, 2 with the values that we want to compare. So these are the quantum register input 1 and input 2. And then we have a specific quantum register called output that we're going to measure here at the end. That will tell us if they are similar or the same, and will tell a measure of the quality. So the most important part of the quantum circuit is the one related to the output quantum register. You see that there are 2 Hadamard gates, a C-swap, and a NOT, and finally a measurement that will tell how the quantum register values differ or if they are identical. But let's start with an example. We have the input in state 0 and input 1 in state 0 and input 2 in state 0, 2. That means that in this case the 2 registers are in the identical state. We have a 3 qubit system macroscopically, so we can represent our circle notation. All the 3 qubits in the initialization are in the state 0, so that means that if you use a 3 qubit system, a circle notation, this is going to be the representation. So our system is in state 0. The second step is to apply on the quantum register another Hadamard operation. We know how to do this in a circle notation. We apply the Hadamard gate to the pairs. There is a stride of 4, so we apply the Hadamard gate to these pairs. That's what we get. So we get superposition of state 0 and state 4. The next step is actually to perform a C-swap. This is a control swap, so there's a control on the output quantum register, and the results of this operation is basically nothing. So nothing happened. We have the same quantum state before and after the C swap. Then we apply another Hadamard gate, and we go back to the initial state 0. Remember that to apply the Hadamard gate is its own inverse, so we go back to the original state. After Hadamard gate, we do a NOT operation on the 3rd qubit. That means that we actually swap this pair. As you can see, then, if we do a measure on the 3rd qubit, it will be always 1. So if we have in input 1 and input 2 the same value, and when we measure, we will always get 1 here. So let's look at an example in the case that input 1 and input 2 quantum register have a different values, 0 and 1. Obviously, we can also check with different values. So this is the realization of the quantum circuit. They both have 0 in input 1 and 1 in input 2. The major difference that you can see here, it might surprise you, is the here. The measurement that I'm going to have in this case might be different. So whenever we have a different values in the quantum register, the measurement in the output register might be different. But let's see in more detail using the circuit notation what's going on here. So we start with initialization and the Hadamard gate. So we start in state 2, that is 0 and 1 in 3-qubit system, and then we apply the Hadamard gate on the pairs, and that results in superposition of state 2 and state 6. After the Hadamard gate, we have a C-swap operation. In this case, the C-swap actually has a tangible effect, and you see that from state 6 we go to state 5, still superposition of 2 and 5 after the C-swap operation. Then finally we apply another Hadamard gate to the results in the output gates, and we see that we have this superposition of state 1, 2, 5 and 6. If we then make Hadamard operation, NOT operation, and then we do a measurement here, we see that if we do a measurement operation in this case on the third quantum register, so here is 0, 0, 1, 1, we see that the probability of measuring either 0 or 1 on the output quantum register is the same, so 50%. So in the case of two opposite quantum state values, then we have equal probability to measure 1 or 0 in the output quantum register. So what we learn by first doing a swap test with identical and then with the different? Well, we learned that if the two input states are equal, the output of the register will always result in state 1. So in the case, if we call fidelity, the so-called input similarity, if the similarity is 1, so that means that is identical, then the probability that we measure will be always 1. However, as the two inputs become increasingly more different, the probability of reading one outcome will in the output quantum register will actually decrease. And then, for two completely different quantum states, the probability of having 1 or 0 in the measurement is going to be 50%. So this is the case where the two qubits in the input register are identical. So we always measure 1. In the case they are completely opposite, different, so diff, and these identical. In this case of completely different, then we have a 50% of measuring either 0 or a 1 state. So we can check the probability that we get a 1 outcome. If we repeat the swap test enough times, we can estimate the probability and also the fidelity. That is a more quantitative measure of how close the two states are. In this plot, we have on the x-axis the required input similarity, that is how equal they are, and then the number of tests or measurement that we need to achieve a certain similarity. This is the last slides, and talk to you soon.